Hi blockchain and cryptography enthusiasts! Welcome to ZK Marek, where I explain all things crypto. Before we dive in, we want to thank the Ethereum Ecosystem Support Program and vLayer for their invaluable support in making this video. In the previous episode, we explored the KZG commitment scheme. The key feature is that it allows us to commit to polynomials. Effectively, we can digest the whole polynomial to a single EC point, commitment C, and verify its value at a certain x0 coordinate with a proof, another EC point. Today, we'll see how Ethereum uses this cryptographic primitive to solve one of its biggest scaling challenges. It all revolves around blobs. To understand blobs, we first need to tackle how Layer 2 rollups work with Ethereum. L2 rollups decentralize computations by building blocks of transactions in a separate Layer 2 network. To prove fraud or verify the correctness of L2 transactions on Ethereum, we need to access them somehow from L1 itself. Of course, storing a whole transaction batch, for example in a smart contract or transaction data, does not scale well. This is where blobs come in handy. Blobs introduced in EIP 4844 provide cheaper storage space than regular transaction data, because blob data is deleted after around 2 weeks. So we don't need to pay for storing it permanently. At the same time, we can still access the commitment to the data blob directly within smart contracts, even if the data is eventually removed from the blob. But how is it possible? Let's dive deeper. At its core, a blob is just a sequence of 4096 numbers. These aren't just any numbers, they're field elements, each one being a number smaller than field prime r. Because this number is large, up to almost 256 bits. Each field element can represent close to 32 bytes of data. This gives a total blob capacity of up to almost 128 kilobytes. That is truly a lot of storage space by blockchain standards. But as we mentioned, it's temporary. How then can we make it accessible without unnecessarily bloating the execution layer? This is where vector commitments come in handy. We can represent these 4096 numbers as a polynomial. How? Let's first take a look at a simpler vector. We create points in Cartesian space by using vector indices as x coordinates and vector values as y coordinates. Now, through these points, we can draw a unique polynomial of degree 3. One of the techniques to do that is called Lagrange interpolation. In general, for a polynomial of degree n, we need n plus 1 points. This new polynomial, evaluated at given x, will return our original data. P of 0 is 30, P of 1 is 9, and so on. We can extend this method to handle longer vectors with more and more points, allowing us to draw a unique polynomial that represents the data. Ethereum blobs use polynomials of degree 4095. And of course, ultimately, we will need a discrete polynomial on the prime field associated with the blob. This polynomial is a mathematical encoding for our blob data. Now that we have transformed our vector to a discrete polynomial, we can use KZG. But first, let's see what kind of prime fields are we dealing with here. The whole setup uses the BLS12 381 curve, with a field prime, P, of order up to 2 to the power of 381. On the other hand, the scalar field for this curve has field prime, R, up to almost 2 to the power of 256. As we mentioned earlier, the blob elements are field elements of the size of up to 32 bytes. This is because blob elements are polynomial evaluations, y coordinates, which are scalars used in the KZG commitment scheme. But in KZG, we also deal with EC points, which for the BLS12 381 curve are up to almost 48 bytes big. It is important to distinguish between the elliptic curve and polynomial evaluation. The elliptic curve is used for KZG encryption and verification, while the polynomial represents the blob elements. So let's put it together. The blob creator converts a blob data into a polynomial and creates a commitment C to it that will be available in a transaction on-chain. Later, he can prove to the verifier, in this case any smart contract, that the polynomial evaluates to a specific value at a given x0 coordinate using another EC point, a proof. As we can represent our vector with a polynomial, now we can commit almost 128 kilobytes of data into a single EC point, which is roughly 48 bytes, and verify that an item belongs to that set with another nearly 48 bytes. Let's see how it works on Ethereum. Consider a block on L1 and a blob field that gathers the batched transaction data. For blob data, a KZG commitment and its hash are created. This hash will be permanently accessible from the smart contracts. On the other hand, full blob data will be accessible on request only for 4096 Ethereum epochs. After that time, the blob is pruned and the data is lost on-chain, although it can be still stored externally elsewhere. But with access to the commitment, we can verify that some transaction data really belong to a blob, even after it was pruned. We mentioned smart contracts earlier. Let's see blob operations in practice. Here is a Solidity pseudocode for a smart contract which verifies the KZG commitment and compares it to blob commitment. We will need the following inputs. The KZG commitment representing the polynomial. The values where the polynomial is being evaluated. The KZG proof for the evaluation. And finally a blob index, which uniquely identifies a blob within a block. First, we pack the KZG input data into a byte array. Next, we use the function that calls the KZG precompile, and with it we check if the proof is verified successfully. Now let's check if our verified commitment matches real blob data. To access real blob commitments, we use the Solidity function blob hash. For a given blob index, it returns the 32-byte hash of the blob within a block. The hash consists of the byte representing version, followed by a truncated hash of the KZG commitment. Blob hash returns 0 if the blob with a given index does not exist. Finally, we calculate the hash of the verified KZG commitment. We require the last 31 bytes of commitment hash to match the blob hash result. Congratulations! We successfully verified a real blob data. And that is it from the blobs. Today we've learned how we can commit to a vector, and next time we will leverage this to dive even deeper. It's time for Verkle Trees. Thanks for watching ZK Marek channel.